Hello everyone. Before we dive into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss our upcoming videos, make sure to subscribe and hit the bell icon to get all the notifications. In the deep darkness of the Orion constellation, where starlight seems suspended between existence and non-existence, a cosmic spectacle is unfolding that feels like the beginning of everything. This is not science fiction, nor historical reconstruction. It is an event we are witnessing now, live, through the sophisticated eyes of two of the most powerful instruments ever conceived by human ingenuity, the James Webb Space Telescope and the ALMA Radio Observatory. The subject? A newborn star, a protostar named HOPS315, which is literally shaping new planets. We are about 1,300 light-years from Earth. In cosmic terms, that's our backyard. But the actual distance is such that the light we see today from HOPS315 began its journey when the Roman Empire was a distant memory, and modern civilization just a distant dream. Yet, what this light brings us is something directly connected to our existence. The origins of a planetary system, the exact moment when cosmic matter begins to organize itself to form worlds. The images and data collected show a protoplanetary disk surrounding the young star. So far, nothing new. The presence of dust and gas disks around nascent stars is a well-known phenomenon. But what makes HOPS315 unique, and truly revolutionary, is the clarity with which concentric structures, rings, and gaps within the disk are visible. These are unmistakable signs of the presence of matter clumps, regions where dust is beginning to collapse under its own gravity, forming planetary embryos. In other words, for the first time, we are witnessing planets being born. It's a vision so powerful that it challenges our perception of time. Because what for us is a photographic moment, there happens on a scale of millions of years. Every particle of cosmic dust takes centuries to migrate, to aggregate, to merge with others until it becomes something more. Yet, with the combined precision of JWST, which captures infrared images, and ALMA, which records millimeter waves from the cold interstellar space, we can perceive differences in temperature, density, and composition with previously unimaginable clarity. Observing HOPS315 doesn't just mean witnessing the birth of a planetary system. It means looking back in time, to the moment when even our sun was just a young star shrouded in a cocoon of dust. The analogies are striking. Around HOPS315, a ring-like structure has been identified that closely resembles what in our system is now the asteroid belt. In that ancient region, primordial debris continued to orbit without ever becoming planets, silent witnesses of a bygone era. And it's precisely in these gaps between rings that astronomers detect gravitational signatures left by forming protoplanets, a void that is, paradoxically, full of meaning. So how exactly do planets form from these turbulent clouds of gas and dust? The process, as fascinating as it is complex, begins with the coalescence of dust into tiny pebbles, driven and slowed by various dynamic forces: gravity, gas pressure, magnetic turbulence. In an unstable and chaotic balance, some of these aggregates grow more rapidly, attracting more material and forming what scientists call planetesimals. Once they reach a critical mass, these cores begin to pull in increasing amounts of gas and dust, accelerating the process toward the formation of a true planet. In this cosmic theater, every detail is significant. The temperature differences between regions closer to the star and those farther out determine which chemical elements can condense and which cannot. Rocky planets, like Earth, form in the inner zones, where temperatures are too high for ice to exist. Gas giants, like Jupiter, form farther out, where the environment is colder and more favorable for accumulating hydrogen and helium. The beauty of the discovery of HOPS315 also lies in the fact that it allows us to test these theories with real data. For years, the birth of planets has been described through theoretical models and computer simulations. Today, for the first time, we can compare those simulations with observational evidence. We can see if the grooves in the disk really correspond to the places where planets are forming. We can study the disk's composition, the distribution of mass, and even hypothesize the presence of stable orbits where, one day, habitable planets might exist. And this is where scientific imagination merges with wonder. Because looking at HOPS315 doesn't just mean exploring a distant phenomenon, but reflecting on our own past. Every ring, every discontinuity in the protoplanetary disk is like a line written in the universal history of world formation. And in those lines, we might one day find answers to our deepest questions. Are we truly unique? Or is what we see out there simply the norm in the cosmos? If what is happening around HOPS315 is indeed common in the universe, then every star we see in the night sky, or at least 1 in 5, according to the latest estimates, could be, or could have been, the beating heart of a similar process. Millions, perhaps billions of protoplanetary disks may have given rise to complex systems populated by rocky planets, deep oceans, dense atmospheres, and maybe, in some cases, life forms. Every observation like that of HOPS315 is not just a window into a distant place. It is a mirror reflecting unimaginable possibilities. There's another fascinating aspect to consider: the brevity of time during which we can observe this process. The visible phase of planetary formation, the one marked by disks with clearly defined rings and grooves caused by planetary embryos, is fleeting. It lasts only a few 100,000 years, an infinitesimal fraction of a star's life. Therefore, catching an object like HOPS315 at the exact moment this gravitational sculpture is happening is an extraordinary stroke of luck. It's like finding a fossil in the midst of an avalanche, a precise coincidence in time and space that allows us to reconstruct events otherwise invisible. But the implications don't stop at pure astronomy. This discovery raises new questions about the nature of matter, the chemical evolution of the universe, and even the origins of life. Even today, the instruments available to scientists can identify complex molecules within protoplanetary disks: water, methane, ammonia, hydrocarbons. Fundamental ingredients that, at least on Earth, form the basis for the development of life. So, is it possible that even at these embryonic stages, some planets are already accumulating in their chemical makeup the seeds of future biology? Observing a system like HOPS315 is like opening a time machine. It tells us not only how planets form, but also what chemical and physical conditions accompany them from their earliest moments. If, for example, we discover that the presence of water is common in protoplanetary disks, we could deduce that oceans and seas like those on Earth are not an exception, but a rule. If instead water turns out to be rare, then our Earth, and everything that inhabits it, would appear even more unique and precious. And it is precisely in this dialectic between universality and uniqueness that the most fascinating challenge of modern science plays out. On one hand, every new discovery seems to suggest that our case is not special. Physical laws are the same everywhere, gravitational dynamics identical for all stars. But on the other hand, the immense variety of possible outcomes, multiple systems, gas giants close to their stars, worlds with elliptical orbits and extreme climates, reminds us just how delicate the balance was that allowed a planet like Earth to develop and sustain life. HOPS315, with its rings invisible to the naked eye yet strikingly evident under the electronic gaze of telescopes, is not merely a celestial object. It is an open question, a natural experiment in progress, a lesson written in the language of the cosmos. And we, observers in a remote corner of the galaxy, are fortunate enough to be able to read it. But also intelligent enough to ask the right questions. What are the next steps? Future observations might reveal even more: changes in the ring patterns, early signs of advanced planetary aggregation, Perhaps even the indirect discovery of already formed bodies just hidden in the chiaroscuro of the disk. With increasingly refined instruments, we could one day directly measure the mass of these objects, define their atmospheric composition, or map the distribution of heavy elements in the disk. In the future, it is even conceivable that we could detect forming planets with sizes similar to Earth's. But perhaps, above all, what fascinates us is the sense of witnessing the inevitable. What does a star like HOPS315 ultimately tell us? That the universe never stops creating. That every grain of dust, even one floating today in the void 1300 light-years away, can become a planet. That every planet can become a home. And that every home, under extraordinarily lucky conditions, can become a world.